Hi everyone, my name is Luigi Filippo Chiara, and today I would like to talk about the paper Goal-Driven Self-Attentive Recurrent Networks for Trajectory Prediction. This is a joint work between Pasquale Coscia, Sourav, Simone Calderara, Rita Cucchiara, Lamberto Ballan and I, from the University of Padua and University of Modena and Reggio, Emilia. Human trajectory forecasting is a key component of autonomous vehicles, social-aware robots, and advanced video surveillance applications. To infer future positions, the main input to any model are the previously observed location, and at its core, this regression task boils down to the prediction of a time series. In this work, we follow the well-established short-term protocol used in human trajectory prediction, that is, to observe 8 time steps and to predict the next 12 time steps. To quantitatively evaluate our model, we consider 2 standard error metrics, namely the average displacement error and the final displacement error. Specifically, since we frame our analysis in a stochastic setting, these metrics are obtained by generating 20 predicted samples for each input trajectories, and then retaining the one that provides the smallest error. To tackle this task, we propose a lightweight, attention-based recurrent backbone that acts solely on past observed positions, which we called SAR. Although this backbone already provides promising results, we demonstrated that its prediction accuracy can be improved considerably when combined with a scene-aware goal estimation module. We conduct extensive experiments on publicly available datasets such as SDD, IND, and ATH-UCY, and show that our approach performs on par with state-of-the-art techniques while reducing model complexity, as it uses strictly less information with respect to other architectures. Multiple paths can occur in the future in specific circumstances, for example, when people are approaching roundabouts or intersections. These situations may lead a prediction model to learn an average behavior with not feasible trajectories, such as the one predicted by the SAR model on the left panel. To overcome this issue, we employ a semantic-aware goal module based on a UNet architecture from a previous work, in order to infer multiple likely destinations that are then fed to the temporal backbone to predict multimodal outputs that are scene compliant. Our forecasting method consists of 2 main components. One corresponds to the temporal attention backbone and 2 to the goal module. SAR only uses module 1, while GoalSAR uses both module 1 and module 2. The recurrent backbone implements a self-attention mechanism and feed-forward layers that solely relies on previous observed position. On the other hand, the observed positions are embedded on a 2D map, and the RGB image is processed with a segmentation network in order to produce semantic classes. The 2 are then concatenated and pass through the goal module, which processes them through a UNet architecture to predict future goals as probability distributions. Final positions are then sampled and fed to the temporal backbone, which processes this additional information in the temporal loop. We tested our models on 3 pedestrian datasets. Table 1 shows our results on Stanford Drone dataset. Our temporal backbone, SAR, performs on par with several recent approaches. In particular, we note that it reaches similar results to PECnet and outperforms both GoalGAN and MGGAN. With the addition of the goal module, GoalSAR is able to slightly improve on YNet results, even though it uses a relatively simpler architecture. Besides, we also report additional inputs used by the different models, which we divide into social, image, and goal component. A, I, and G. Our SAR models does not use any of these elements, as it relies only on the temporal component. These results prove the beneficial effect of encompassing goal information with a self-attentive mechanism, and that several approaches do not properly exploit the additional input image and social information when dealing with complex scenarios. Table 2 shows our results on the intersection drawn datasets. These results are in line with the previous table, confirming the effectiveness of our architecture. Table 3 reports quantitative results for our methods on the traditional ATH-UCY benchmark. A similar trend with respect to the previous tables is outlined, with SAR performing on par with PECNEC and outperforming both GOLGAN and MGGAN. It also outperforms by a fair margin Transformer TF, which uses the standard encoder-decoder transformer architecture. This proves the effectiveness of our simpler network in modeling temporal sequences. GOL-SAR performs on par with Trajectron++, AgentFormer, and YNet, reaching the second best average ADE and FDE. Here are some qualitative results obtained with GOL-SAR. The first row shows a few examples of easily predictable trajectories on different datasets. The second row highlights the multimodal behavior induced by the goal module. The highlighted example, in red, shows a failure case, where, due to a sudden direction change, our model fails to predict the future positions. In conclusion, to predict future human positions, we propose a simple yet effective attention-based recurrent architecture that processes temporal dependencies. When combined with a goal estimation module, our model is able to estimate likely trajectories with an increased multimodal capability. Finally, we emphasize the fact that our architecture is fairly uncomplicated, does not leverage social information, and scene knowledge is only processed in the goal module. Despite using less information, the proposed approach performs on par with many state-of-the-art models and even shows slight improvements in some scenarios. Thank you for your attention. For the code, pre-trained models, and further information, please visit our project page.